record it, but so yeah, bond strength, bond polarity for sure, are going to make a difference in how easy it is for water to pull off that proton, or any base for that matter. It doesn't have to be water, but any base. The water is the base for Ka. Anything else?
Would temperature be a factor? Speeding up the molecules?
Well, we're going to keep this all at the same temperature, 25 degrees C. Hmm?
Strength of the conjugate.
Yeah, the strength of the conjugate base. And so let's say, the products, the more stable the products, the bigger the driving force. And so that has to do with the base. So the conjugate base stability, let's say. The conjugate base stability, we look for a couple of things in conjugate base stability. One, we look for charge localization, delocalization. There are things that can affect the amount of localization of charge, and those would be things like the inductive effect. Inductive effect is usually minor. The major one, if it's present, would be resonance delocalization. So resonance delocalization is a bigger factor there. Other factors would be hydration or solvation. Since we're looking all at aqueous, hydration, because we're looking at how well the conjugate base is hydrated by water, because the conjugate base is going to have some negative charge. It loses a proton, so it's got to have some negative charge. And that negative charge can be stabilized by surrounding with water molecules, waters of hydration. For you guys who are doing the base, base strength, the stronger the base, the higher the negative charge localization is. The weaker the base, the more that negative charge is spread out through the structure. And so we're going to use Spartan to examine the charge localization or delocalization. All right, was there anything else?
Yeah.
Forget something?
I have a question. Why does the conjugate base stability influence the acid strength?
Oh, because it's a driving force. The driving force is you want to go from stronger to weaker.
Mm-hmm.
And the weaker it is, the more stable it is. And so we're just going from less stable to more stable. And so one way of talking about stability of the products is just to look, what makes one base more stable than the other? If I were to give you two bases, like acetate versus ethoxide, which one is more stable and why?
The acetate.
Why?
The acetate is more stable because it's a weak base, and the pentoxide.
Well, that's a little bit, okay. That's fine. That's called consult the chart method. You just look at the chart, you see, okay, acetates are more stable than ethoxide.
Wait, ethoxide?
Ethoxide. Ethoxide is probably not a base you've heard of.
Sulfides are not stable.
Okay, how about sulfide versus oxide? Two bases you've heard of. Sulfide versus oxide. Which one is a more stable base, and why?
We don't know. Because they're both unstable.
Sulfide and oxide are both unstable, but which one's more unstable?
Sulfide.
Well, that's why we're talking about this. We're talking about this because we don't have to look at the chart. Maybe we could just figure it out ourselves. You know, I say that it's not sulfide. I would say that sulfide is more stable than oxide. I'd say oxide is less stable than sulfide.
Because the product is HS. Because of HS?
Not because of its conjugate. You know, that's the way you learn it in Chem 1A. You learn, okay, the stronger the acid, the weaker the conjugate base. But what we're trying to do here is we're trying to understand it structurally. So what structurally is different between oxide and sulfide that makes sulfide more stable? Yes. Oxygen has a higher charge density. Oxygen is a smaller atom, same charge. Therefore, the charge is more localized in smaller volume than sulfide. And so, you know, this is why we're looking at this, so we can see, because, you know, the more stable the product you form, the more likely or the better driving force you're going to have for that particular reaction. But going back to this, am I missing anything? Well, I think that's about it. All right, so we could take a look at some acids like this. For example, HI, HBr, HCl, HF. Yeah, these are strong acids. All of these are strong acids except for one. Which one is it? HF. HF is considered a weak acid, but the rest are strong. Out of these strong acids, which one is the strongest? HCl? Well, we get conflicting. When we look at the bond strength, you know, and we look at HI versus HCl, you know, which one is a stronger bond, which one's a weaker bond? You know, so which one's a weaker bond, HI or HCl? Let's say HI is a weaker bond. Why is HI a weaker bond? Bigger atom. Bigger atom. And so we can use valence bond theory to try to understand. Valence bond theory is based on Lewis structures. So if we look at HI, HI has a Lewis structure like this. With valence bond theory, what is a bond? How does valence bond theory describe what a bond is? Not transfer of electrons. Orbital overlap, right. And so what orbitals are overlapping in this bond?
The S and the sp3.
Yeah, this would be an SsP3. So we got S, and iodine's a big atom, so sp3 is going to be quite big on iodine. And so this would be an SsP3 orbital overlap. When we look at the electronegativity difference between iodine, you know, which one would you expect to be more electronegative, iodine or hydrogen? Well, hydrogen has a decent electronegativity. You know, we can look at Pauling's chart and see, but there's not a huge electronegativity difference actually. We'll just say the charge density, the electron cloud. You know, electron cloud is going to be pulled towards iodine or pulled towards hydrogen in this case. That's a hydrogen S a little bit. I shouldn't write the H like that because some people think. The nucleus of that's right. So, yeah, pull towards hydrogen. Well, we can pull towards well, let's look at HCl. What's the difference between an HI and HCl? Well, the difference is in the size of the sp3 orbital. The hydrogen's asked to be small, but Cl has a much smaller sp3 orbital, right? It's a much smaller atom. The electron density is more concentrated. What holds these two atoms together? Tell me what holds the two atoms together in a covalent bond. This is going to be more polarized. You know what polarized is? Polarized means the electron cloud is distorted towards chlorine, or polarized towards chlorine, because chlorine has much higher electronegativity than hydrogen, and so it's capable of pulling more electron density towards it. But anyway, what holds two atoms together in a covalent bond like this, according to valence bond theory? A lot of people say the overlapping orbitals hold them together. So you think, are the orbitals, do they have Velcro on them, and when you attach them, they stick together? Or why do the orbitals stick together? You know, you got one orbital here with negative charge, you got another orbital here with negative charge. They should be kind of repelling each other. So why are the orbitals overlapping? How's that going to hold the molecule together? Yeah, basically the orbital overlap gives you a higher probability of finding electron density in the internuclear region along the internuclear axis. With that concentrated electron density, we got the positive nuclei being attracted to the negative charge cloud here, and that's what's going to hold it. So it's a positive nuclei being attracted to the extra electron density in the overlap region. And well, anyway, the HCl is going to be a stronger bond. And so the bond strength goes like this. You know, HF should have the strongest bond, followed by HCl, HBr, and HI. But as far as polarity goes, you know, the most polar of these will be HF. You know, HF, fluorine has the highest electronegativity, so it's going to withdraw most of the electron cloud towards it. And what that does is it results in a delta plus here on the hydrogen and delta minus here on the halogen. And so as far as polarity goes, you know, HF is the most polar, right? And HI is the least polar. And so in terms of bond strength, we should see increasing acid strength this way. In terms of polarity, we should see increasing acid strength in the opposite.
Wait, but excuse me, how come HI is a stronger bond?
HI is a weaker bond. HCl is a stronger bond. Because they have more negative charge density concentrated in a smaller volume. It's going to result in a greater electrostatic attraction.
But it says increasing acid strength as you go up.
Yeah, because the weaker the bond, the easier it is for somebody to take the hydrogen. So example, water comes along here, it can more easily pluck this hydrogen, the proton, off HI than it could pluck it off HCl. If you're a water or base trying to pluck this off, it's going to be more difficult because of the more concentrated negative charge. You're going to get into a tug of war. As oxygen's sp3, a lone pair, oxygen has an sp3 lone pair on it. And this sp3 lone pair, right, has a pair of electrons here. And so you get in a tug of war here. So this oxygen is trying to overlap with this hydrogen and break this off. So do you see? Versus up here, if we get in a tug of war up here, it'll be a little easier. So oxygen comes in here. And then another lone pair. So sp3 here on this oxygen comes in here. It's going to more easily overlap with this S and kick these sp3 out, right? This sp3 comes in here, overlaps with this S, it's going to have a harder time because there's going to be a more substantial tug-of-war between these two. Even though it's a more substantial, water is still going to win easily because that's a strong acid. Right? The water comes in here, it just overlaps this, kicks out those. Right? The sp3. So looking at HI is just going to be easier for water to come in there and pluck off that proton. Right? And so HI should be the strongest of this series. But in terms of polarity, the thing is, water is delta minus. And so the delta plus on this hydrogen is very small, so there's only a very weak attraction here. Whereas there's going to be a much stronger attraction here in HCl because this delta plus is much bigger. But nonetheless, even with this weak attraction, the collisions are there, and so it can easily abstract it. And so it turns out that this attraction isn't an important factor because which one's the dominant term? Is bond strength is the dominant term. In other words, that polarity is enough to attract a water to it. And so the bond strength is the most important factor that we look at. But this is about 1 million times weaker, 1 million times weaker than HCl. And so true or false, HF has a bond that's 1 million times stronger. If it's 1 million times weaker than HCl, then it must have 1 million times stronger bond, right? And so if HCl's bond strength is about 400, let's say 300 to 400 kilojoules per mole, then HF's bond strength must be 300 million to 400 million kilojoules per mole. True or false? No way. I mean, that's ridiculous, right? 300 million kilojoules? That's crazy. And so why is HF 1 million times weaker? HF is 1 million times weaker because of ion pairing. So that bond can be broken, but what happens is this. HF is a little unusual because HF and well, let's see, how should I do this? Let me do it without the waters to show it. So HF breaks up into H plus and F minus. Well, the problem with H plus and F minus, or hydronium and fluoride, is they don't quite separate completely because fluoride is got a lot of negative charge density in a small volume because fluorine is quite small. And so there are actually two steps. We don't produce free hydronium. In order for this solution's pH to drop, we need free hydronium because that's what we're going to measure. And so what happens is this has to undergo a second step in order to break these. So there's got to be another collision, and finally the H plus can be broken free from the fluoride minus. And so now we have the free ions. And so this is the ion pair that greatly reduces the strength of each other. Whereas chloride, the ion pairing with chloride is less severe because, why? Chloride's a lot bigger, right? Not as high of a charge density. All right, so it gets tricky because we have these competing, sometimes these are competing factors. So for this lab, we're going to keep the bond strength the same. That is, we're only going to look at one type of acid. The type of acid we're looking at in this lab are the oxyacids, right? In other words, all of them are going to have HO bonds.
hypochlorite.
That's although yeah. So let's look at some oxyacids. For example, CH3CH2OH versus CH3COOH. This is ethanol versus acetic acid. Right? We know ethanol. Is ethanol good at neutralizing bases like sodium hydroxide? No. Ethanol, you know, if you look at the chemical properties of alcohols, you know, they're pretty much all, you know, redox. They can undergo a few other chemical reactions, but primarily known as just a fuel. Whereas acetic acid, yeah, is an acid, amongst other things. And so this is what we're looking at, this type of thing we're looking at today. And so what about ethanol? Ethanol has an HO bond. Acetic acid has an HO bond. Ethanol is so weak, it's considered neutral, or considered, I mean, it could react as an acid, but you'd need a very powerful base to do it. Considered neutral to extremely weak acid. If you have some super base that'll pluck off that proton. This is, you know, just a weak acid. But ethanol is going to be much, much weaker than acetic acid. Acetic acid is a much, much stronger acid. But the bond strength is the same. When you look at the electronegativity difference, it's the same too. You know, hydrogen is a 2.1, oxygen is a 3.5, you know, on the electronegativity scale. And so what's the difference here? Yeah, we have to, if this is the same, then we look deeper into the structure, right?
Yeah, later.
When we look deeper into the structure, we can look at this based on the inductive effect. The inductive effect says this. The inductive effect is just draw arrows. So we start drawing arrows. Which one's more electronegative, oxygen or hydrogen? Oxygen. So we draw an arrow like this. We got an arrow like this. Which is more electronegative, carbon or oxygen? Oxygen. So we draw an arrow like this. But these two carbons are not the same. And they do not have the same electronegativity. Do you know why? They are not the same. You know, what is carbon's electronegativity? Carbon's electronegativity is 2.5 on the Pauling scale. This might be close to 2.5, but this is nowhere near close to 2.5. Why are the electronegativities so different? Well, not the formal charges. The formal charges are both 0. Well, normally in Chem 1A, you're taught this. You're taught that, you know, we have this inductive effect here with the terminal oxygen. But right now, we could see that there's going to be a big difference in those two carbons, because what's the oxidation state of this carbon versus that carbon? Tell me what the oxidation state on this carbon is.
+4?
No. It's not +4. Not -2. -2 is close, but not -2. That carbon. -1. Yeah, -1's correct. You know, -1, that carbon's already kind of electron rich, right? It's not going to be nearly as electronegative. What's the oxidation state on this carbon here? +3 is correct. +3. Do you see those two carbons are totally different? Totally different. Which one do you think is going to be much more electronegative? +3. The oxygens are the same at -2. And so if there is something that's going to happen, what's going to happen here is when there's a tug of war for the electron density between carbon and oxygen, carbon is going to pull a lot harder here than it is here. You know, it might not be a reverse like this, but nonetheless, it's going to pull a lot harder than this carbon does in a tug of war. And that's because this oxygen here is pulling electron density away from the carbon. That's the difference between these two carbons, and one's got another oxygen attached to it. And so this is the inductive effect here. And what that does is it means the electron cloud is going to be quite a bit more polarized. And so the primary difference in the acid strength between these two isn't and so we could draw the electron cloud being polarized here. And so electron density sucked towards this terminal oxygen here, whereas over here the electron density is going to be pulled towards this oxygen here in the middle. And so there's going to be a difference in terms of the delta plus that results here. The delta plus that results here on ethanol is much smaller than the delta plus that results on acetic acid. And so the base is going to be much more attracted to acetic acid than ethanol. The bond strength is going to be about the same because there's sp3 on oxygen and an S on hydrogen, sp3s, single bond. When we try to visualize the electron density, the electron cloud, you know, this is one way we could do it using Lewis structures. Another way we could do this is by using Spartan, which is quantum mechanics. And what's the difference between valence bond and molecular orbital theory? The way a bond is described. They're both based on quantum mechanics, right? Molecular orbital theory and valence bond theory are both based on quantum mechanics. And so if they're both based on quantum mechanics, then why do we need two theories? Why don't we just use one bonding theory? Just call it quantum mechanics. What do you tell me? What? Hmm? Yeah, valence bond fails, so why don't just get rid of valence bond? Just use quantum mechanics, because quantum mechanics doesn't fail for something as simple as O2. Uh-huh.
But sometimes valence bond works too.
Yeah.
So don't get rid of that theory. Sometimes molecular orbital wouldn't work.
Sometimes molecular orbital wouldn't work. Why?
Wait, molecular orbital always work?
Always works. Yeah. Valence bond theory fails. Molecular orbital theory should always work. So why not just get rid of valence bond, the one that doesn't work sometimes? Just use the one that always works. Dave.
Harder to work with quantum mechanics?
Yeah, it's just harder, right? We called it, valence bond theory is much easier. And so what we could do is we could easily visualize what's happening with electron density here. I mean, we could draw out the orbitals and stuff if we want. You know, here we got a carbon and an oxygen, and sp2 sigma bond, right? And then we got the pp pi bond here, pp pi bond. And then we got some sp2 lone pairs out here, sp2. And so it's easy to see what's happening with electron cloud because we know that oxygen is more electronegative, so it's going to skew both the sigma bonding electrons towards oxygen, and the pi bonding electrons should be skewed towards oxygen as well. And so we get this polarization of the charge cloud. The lone pair should be being pulled in towards oxygen, like this. Lone pair. So it's easy to come up with an electron density map, right? Based on valence bond theory, because it's not all that complicated. Here we got an sp2, sp3 sigma bond here. And we said that this carbon is unusual because this carbon is going to be +3, so it's going to suck more electron density from that oxygen, making this oxygen even more electron poor, which means it's going to suck more electron density from the bond here to hydrogen, right? This one is be more polarized. And then we got the lone pairs on oxygen. And so it's not that difficult to kind of come up with a quick valence bond electron density map. And whereas in quantum mechanics, it's going to be much more difficult. We need a computer to do it for a molecule like this to figure it out. And then we look at all the orbitals, and then we look at the combined. And so what we're going to do is we're going to draw out the Lewis structures like this and get an idea of the electron density like this. And then we're going to build these molecules in Spartan and then compare the electron densities. In Spartan, we're going to generate a map, an electrostatic potential map, in which the positive regions are marked in blue. You know, they don't show it like I showed it here. They mark it in blue. That's because, you know, it's lacking electron density, and so we don't have the electron density. That positive charge goes right unbalanced. And so the positive regions are in blue. The negative regions are going to be in red. The kind of neutral regions will be green there. And so on the one hand, well, how big of a difference is this delta plus? Is it huge? I mean, as far as this is so many orders of magnitude stronger than this. Well, it can't just be the polarity. There has to be other factors influencing the difference, because it's such a huge difference in terms of acid strength between ethanol and acetic acid. And therefore, we should look at the products. You know, how stable are the products? Take this off. And so here, the polarity bond strength is about the same, he said. Polarity shows that acetic acid is stronger. But let's look at base stability. The conjugate base. All right, the conjugate base of ethanol, if ethanol loses that proton, it forms the base. This base is called ethoxide. Ethoxide is a powerful base, like hydroxide. You'd expect it to be like hydroxide because it kind of looks like hydroxide. You know, carbon has about the same electronegativity as hydrogen, and so the amount of negative charge density on this oxygen is just like hydroxide. This would just be like hydroxide. Versus acetate.
Is hydroxide unstable?
Hydroxide's unstable, yes.
Ethoxide.
Ethoxide is unstable, highly unstable. Ethoxide. And so for you, past my former Chem 1A students, you guys are going to do the bases. You're going to build the bases and then look at the negative charge density on the oxygen and see how it could be delocalized into the structure. Okay. And here we look at these two, and they look the same, don't they? I mean, carbon's about as electronegative as hydrogen, so this looks like, hydroxide, HO, hydroxide, similar in terms of electron density. Well, the same thing here, isn't it? Carbon's about as electronegative as hydrogen, therefore this is like an HO bond, which means that both of these are like hydroxide. correct? No, no, you know now, you look at those two carbons are totally different. You know, one carbon we call kind of an electron pusher, electron pushing group. The other carbon we call an electron sucker or electron withdrawing group. And so if you look at this one, this is kind of an electron pusher because look at the next carbon over. What is the next carbon over from this? What's its oxidation state here? Not 0. -3. Yeah, this carbon's -3. This whole group, this is called an ethyl group. This ethyl group is electron rich. It's good. This one's going to be a -3 also, but this one's got a +3 here. So this is electron sucking group. It's pulling electron density. This is electron pushing group. Well, the same thing can be said over here. We want to stabilize that negative charge, you know, because this negative charge is creating the. And so on the one hand, we have the inductive effect. The inductive effect looks at how can this negative charge be delocalized in the rest of the structure. Well, it's not going to be delocalized here because this carbon is a -1. Does this carbon want more electron density? No, I mean, it's already got negative charge here. Negative repels negative. It's going to push it away, right. It's not going to withdraw any electron density. Whereas over here, this is a +3. And so some of that electron density is going to be sucked into the structure via the inductive effect. But the inductive effect, you know, is going to reduce the charge a little bit. And so over here, this is going to stay a full negative charge. This is going to have its charge reduced a little bit by having the carbon withdraw some electron density away from the oxygen. But inductive effect, is that the major factor for bases? What's a more important factor for bases? No, a more important factor when you're looking at base strength, more important than the inductive effect that I just said. Resonance delocalization. Resonance delocalization is going to play a more significant role than the inductive effect. Even though the inductive effect, this looks good, right? Because this is going to suck electron density. And base strength is going to depend on how much negative charge. The more negative charge you have, you know, the easier it is to pluck a proton off, a H+ off, right? But this one, we know acetate has another resonance form. And the other resonance form looks like this. But we know that this is a limitation of valence bond theory because which form is correct? Neither is correct, actually. What's correct would be the hybrid. And so we would draw the resonance hybrid for this. Right, in which both carbon-oxygen bonds are exactly the same. Right, and we have something like this. Where one lone pair is smeared out over both oxygens, and 2 lone pairs are fixed permanently. And so each of these has a bond order of 1.5, right? And the charge that results on each oxygen is not -1 on one, it's -1/2 on each. And so which one is going to be a more powerful base? Well, not only do we have a -1/2, but we also have the inductive effect here occurring. And the inductive effect here is we got this +3 carbon here sucking electron density away. And so it goes down to -1/2 by resonance delocalization, and then the inductive will further decrease it, meaning that acetate is a very weak base, right? weak base is very stable. So acetate's a very stable product. And so, you know, it's not, in terms of polarity, I mean, in terms of, you know, polarity, it doesn't quite explain the huge difference in acidity. But when you look at the conjugate base, then it makes much more sense. Why ethoxide is such a weak acid, you know, compared to acetic acid. All right, and so what we're going to do is, you know, we don't, when you build something in quantum mechanics, you don't get this resonance. Are we going to generate two resonance forms using quantum mechanics? In other words, are we going to generate two resonance forms, not using quantum, using molecular orbital theory? No, molecular orbital theory is just going to take us straight to the hybrid, because we're dealing with molecular orbitals, and we have molecular orbitals that encompass the entire molecule. So. Okay. But anyway, molecular orbital theory is too difficult to do by hand for polyatomic species. You know, diatomics is manageable, but maybe some triatomics is manageable. But when you get into bigger species, it becomes less and less manageable. But you know, we don't all have access to a $5,000 quantum mechanics program. So what we do is we just make use of valence bond theory and doing it by hand, right, on paper and pencil. But this will be good because we can compare. You know, when we start drawing structures like this and start drawing these delta pluses and delta minuses, you know, how do we know how good that is? Well, we can compare it to what we get from molecular orbital theory using Spartan. So what we're going to do is, in Spartan, we can actually click on this atom and see what this charge is. You know, we can click on various atoms and see what the charge is, and then get a kind of a comparison, you know, between a full quantum mechanical approach versus our pencil and paper approach. You know, is it worth spending the extra $5,000 for the numbers you get from quantum mechanics? Well, probably. We'll see.
Time noise, yes.
All right, so we're going to be looking at a number of acids. You know, benzene rings are kind of weird species because, you know, when you look at a benzene ring, you might think, you know, it's like a hydrocarbon. All hydrocarbons are kind of electron rich and electron pushers, right? Hydrocarbons are good fuels. And so benzene is a hydrocarbon as well. But benzene and these acids are kind of interesting. You'll see that when you build the structure of benzoic acid or phenol. In fact, phenol is very interesting because, like, you know, most alcohols are kind of neutral, right? You don't use alcohol to neutralize bases, except for phenol. Phenol is about as acidic as...
It's really weakly acidic.
Phenol is actually, I think phenol is more acidic than acetic acid. So I don't know if you want to consider that weakly acidic, but to me, phenol is an unusually strong acid. It's still weak because it's like acetic acid, but it's unusually strong because of what it is. It's an alcohol that is about as strong of an acid as acetic acid. Now that's weird. Why is that? Is it because of polarity? You look at this and you go, is it because of polarity that this is... It can't be because of polarity, I would think, because... Well, let's draw phenol more properly. Phenol, this is the shorthand way of drawing phenol. The longhand way of drawing phenol is like this. So this is an unusually strong acid because it would be thought to be neutral because it's an alcohol. And so I wouldn't think polarity would do it because, you know, we looked at a +3 carbon, a -1 carbon. This carbon here, do you know what the oxidation state on that carbon is? +1. Okay, +1 means it's going to be a electron withdrawer. There's going to be some inductive effect, right? But the inductive effect wouldn't be as severe as something like acetic acid. Acetic acid had a +3 carbon on there, right? This is a +1 carbon. And so there's got to be something more to it that's causing this to be a much stronger acid, and that must be what?
Resonance delocalization.
Well, no, well, let's just, we don't know if it's resonance delocalization. Yeah, we're just going to say it's got to be due to the conjugate base. The conjugate base must be unusually stable, right? But when you look at the conjugate base of this, you know, the conjugate base would be called, do you know what the name of this is? Try to take a guess what the name of this base would be. If this is called phenol, then this is called
Phenolphthalein.
no, not phenolphthalein.
Ooh.
It's a simple pattern. Look at ethanol. Ethanol makes simple pattern. Ethanol makes ethoxide. Phenol is going to make phenoxide. Yeah. So the phenoxide or whatever you want to call it.
What about an open?
Yeah, you look at this and you go, this, how can I have resonance? Because I know in the benzene ring there's resonance, right?
Yeah.
And so the other resonance form is you just move the double bonds. But how is that going to impact the negative charge delocalization or localization on oxygen? Because this negative charge looks to be localized on the oxygen. But have you done, I know I had my class do non-equivalent resonance forms. Have you guys done non-equivalent resonance forms? That is resonance forms that don't have all the same energy?
No.
Yes? All right. Well, this resonance form, you know, if I look at the resonance forms for the benzene ring, that's going to have the exact same energy. But there's another way we can have resonance here. And the other way is it's not going to look like the same structure. If I drop a lone pair into this and make a double bond here, and then this, what's the hybridization on this carbon? This is an sp2. I'm going to convert that into an sp3 and put this pair of electrons into an sp3 orbital. And so we'll go from an sp2 carbon to an sp3 carbon. And so the resonance form is going to look like this. This resonance form is, you know, going to have a higher energy, I would suspect. But and it doesn't look so good, but it's possible. And so what I did was make a double bond here, convert this into a sp3, and then put that lone pair, and now this carbon's going to have a negative charge here. This would be a non-equivalent resonance form. This one's going to be higher in energy. And so when we look at the resonance hybrid will be a weighted average, you know, a weighted hybrid. And that is, you know, the most stable of the resonance forms would have greater weight than the less stable ones. If you did nitrous oxide, then it was like an 80-20 kind of deal. All right, so that's one. The other one we can have is if this lone pair gets pulled here, and then convert this, it gives us another possibility. How many more resonance forms can I draw? What do you think would rather have a negative charge, the oxygen or the carbon?
Oxygen.
Oxygen. And so I suspect this would have a higher energy. Plus, we're breaking up. Remember, benzenes are usually stable because of the delocalized pi bonding network. This is called an aromatic hydrocarbon. And so those pi bonding, because all the sp2 orbitals line up, the entire pi bonding electrons can be delocalized over the entire ring. That leads to an additional stability, because if you look at the bond order of the hybrid, the bond order is 1.5, but the bonds are much stronger than 1.5 bonds. And additional strength is due to the complete delocalization of the pi bonding network over 6 bonds. That's what we have. We don't have to do that in MO theory, but anyway, this, if we go back to this, then we're back to the original structure. And so we can draw a total of 4 resonance forms for this. 4 resonance forms. The hybrid would be biased towards this one. This would be a greater contributor, hybrid structure. And so, you know, and typically hydrocarbon groups are electron rich. They're electron pushers, not electron withdrawers. But something like a benzene ring could be more of an electron withdrawer than an electron pusher. You know? And so we'll see that in our Spartan calculations. And so you're going to look at, you know, at this. As far as Spartan, the data we're going to get are different. One of the pieces of data would be the red. You know, when we look at the electrostatic potential map, we look at, you know, how concentrated is the red, because the red shows a buildup of electron cloud or electron density compared to blue regions. Blue regions are absence of electron density. So, and then green regions are it's even. It's good. Yeah. Okay, that's one. We can look at the map overall, see how the electron density is spread out over the entire structure. And then 2, we can actually look at the individual charges on the atoms. You know, because in our Lewis structures, all we get is delta plus and delta minus. We don't have a number associated with that. You know, we could get a number. You know, there are measurements that you can take, like, you know, debye. You measure the dipole moment in debye and then figure out the delta plus and delta minus on those. You know, but we aren't going to do any kind of experimental work on dipole moments. Instead, we'll just grab those off Spartan. All right, any questions on this? All right, for you guys who are doing the bases, then you'll just draw out the Lewis structures of all the conjugate bases and just build those. When you have a negative charge on the structure, you have to click an extra box saying a negative charge is allowed on the entire structure. Okay. We'll do that. Okay, we're going to go over to Chem 108 then and do a shot. Let's see.